Hey, in this video we will learn how to create a row major representation for a compiler, with example. Have a look at this first example. We will learn about it now. This we imagine the 2D array look like, in the form of row and column. In this example, we have 3 row and 4 column. The row and column numbering is given from 0 onwards. The elements I have taken inside of it is in accordance with the row and column order. Take a look at it. Row numbering goes first and then column number. I hope you pretty much got the idea, what we are going to do. This tabular representation of array is easy to visualize and understand. But this convention is only for understanding purpose, it does not go fit with the compiler design inside the memory. Instead, this is how the actual representation looks like. The compiler map each elements row by row. Have a look at it. The first 4 element of row 0 is mapped first, then the other element of row 1 and then at last all the element of row 2. The idea is pretty much easy to understand, don't get confused. While mapping the element row by row, the compiler would map elements of a 2D array exactly the same way as shown. So we now know how the mapping would take place inside the memory. Good job! Remember L0 means base address, in this case we have taken 200. And W means the size of the memory, in this case we have taken 2 bytes. So base address is starting from 200, and each memory allocates 2 bytes of space for storing elements in them. I hope the explanation is quite clear for you to understand and learn how the compiler would design it row major representation internally. Now let's see some example and devise a general formula for the row major representation to work. Take a look at it. First example, we have taken A of 1 2, let's find out how to devise address for it. Start with base address and add it to 1 multiplied by 4, add it with 2 and multiply them with W. So how do we know it? Let's understand this in detail. As you can see, in order to reach A of 1 2, we need to skip the first row that is having 4 elements in it, so that is why we wrote 1 multiplied 4 and the next part which is, we wrote to add 2, because after reaching the second row, from there we need to take 2 steps, in order to reach A of 1 2, and at last we multiplied it by W, because each memory byte is 2. Did you get the idea of how we are writing the address, by using the following steps as shown? For any queries, comment down your thoughts below. So coming back to the explanation part, we have taken base address as 200, plus 1 multiplied by 4 plus 2 and whole multiplied by 2 gives 212 as our final address. You can see, in the memory for element, A of 1 2, we can find it, present at address 212. Okay, now let's move to our next example, which find the address of A of 2 1. Look at this, it is present here, let's devise an address for it. In order to reach there, we need to skip 2 row, which is having 4 element each in it. And after reaching there, we need to move 1 column ahead, and finally we reach our destination. So, in order to write a formula for it, we use the base address, plus 2 multiplied by 4 and then added 1 to it, and at last the whole result multiplied by 2 byte of space. As you can see 200 plus 18 which gives 218 as our result. And we can find our element A of 2 1 at the address 218, so we got it right. So in order to devise for any index A of ij, we need to find a general formula for it. The general formula would be like, base address that is L0, plus I multiplied by n which is the dimension, plus the index j and whole result multiplied by W which the size of each memory byte. Here the dimensions are 3 rows and 4 column, so m is 3 and n is 4. It is pretty much clear. Take a look at the 2D representation diagram for it. This is how we find the row major representation for any index A of ij. Remember, in row major, we move from left to right way. If you found this video useful, then subscribe and like this video, to learn more about advanced DSA concepts, with clear examples and techniques.